Alright, today we'll talk about Newton's laws, and then we'll talk about relative motion a little bit. If you guys remember, I'm sure you've studied Newton's law of universal gravitation. So what it says is, there is a force of attraction between any two bodies, and the force of attraction is directly proportional to the product of their masses and inversely proportional to the square of the distance between. So what you have is, you have this F is equal to, or F is proportional to M1 M2 over R square. Right? Now you have to think about two masses. This is M1, this is M2, this is the distance between them. This is the first case where you should learn to apply Newton's law or vectors. Okay, is force a vector or a scalar? Does force have a direction? Yes. Force always has a direction, right? So if you're talking about, if you define this R as distance between, or not distance between, you can define R as the position vector of M2 with respect to M1. Okay? So what direction would R be? If I do this, this would be the R direction. You understand? And you have to think about it from the center of this mass M1. Right? So the force of attraction on M2 with respect to M1. What is the force of attraction of M2? In what direction is the force acting on M2? Due to M1, what is the force acting on M2? Towards M2. Right? Towards M2. Or towards M1.
Towards M1.
Towards M1. This is force of attraction of M2 with respect to M1. Correct? So M1 is attracting M2 here. So if you want to define the motion, you are going to say F is proportional to, or F is proportional to M1, M2 over R. Huh?
If M1 comes first, well, M1 is bigger, or?
I mean, it's just, the other way is also true. So this is, you can say this is 1, 2. Okay? So you have F2, 1 as well. F2, 1. Proportional to 1 and 2 over R. So this would be which one would be negative? The first one would be negative.
Why is that?
Because what you have done is if this and this are in opposite direction. Right? So that one would be positive. So that is how you use vector.
So it's like the center of mass and the origin.
Center of mass of the origin. It depends on how you define this R. If you define this R as the position vector of M2 with respect to M1, and you are interested in what is the force of attraction on M2 due to M1, which is in this direction, then this is how it goes. F21 is just the force of attraction on this is F12 and this is F. Okay. Now if you want to complete this, what you do is you introduce something called, so you have these two. Have generally you can say Fg is equal to G M1 and 2 over R square. So for now, just ignore this. We'll again discuss this. Okay, the vector aspect when we do the two-body problem. But for now, focus on this. The force of attraction is when you remove that proportionality sign and put it equal to, you have to introduce a constant of proportionality. Here this is G. G is the universal gravitational constant. It's a constant for a given set of bodies. Okay. So in the same context, if you have, this is how you define weight. Okay. So weight is so what is here? This m is what? Mass of and this R is distance between body and center of force. Okay. This center of earth is very important. A lot of times we may tend to take this from the surface. It's from the center of. And what we do is we generally do this as so this G M over R square. We just use this symbol. W is G. Okay. This is a constant. Do you realize this is a constant? Mass of Earth is constant. G is constant. This R is also practically constant. Assuming your Earth is a perfect sphere, this R is constant. So regardless of where you measure your weight on the surface on Earth, it will practically be the same. Technically, if you measure your weight at sea level or at some altitude, this is going to change. This R is going to change, right? So you may feel a fraction lighter if you measure your weight at a, let's say in Denver or at on some mountain. Or understand why? This G is much higher. This R is much higher, right? So if you go deeper and deeper, this R becomes smaller and smaller. So what is your weight at the center?
Heavy.
Huh?
You're heavier at the center. Well, no, it becomes zero.
This becomes 0, but this becomes
Zero. Undefined.
what does this become?
Bigger.
Hmm?
Bigger.
It becomes infinity. So your mass actually becomes infinite. And that is what happens in black holes.
And that's why you stretch when you go into a black hole.
Now that's different. That's the force. What happens to this R as you go to the center of Earth? Smaller, smaller. It becomes 0, right? At center of Earth. If this becomes 0, what happens to this? G. It becomes infinity. Something over 0 is infinity. Right? So this is infinity. So it doesn't matter what your mass is. Your weight will be infinite. The center. So this is about Newton's law of universal gravitation, and this is very important. This is again where all our orbital mechanics starts. Okay. Now you have to understand something. When we are doing as engineers, our source is what? When you want to solve a problem, what is our source? How do you go about solving the problem? How do you make an engineering problem? How do you, if you're given a real world problem, as an engineer, how do you approach it? Huh? Even before that.
Person got you know very see all the what's the word?
So, knowing? So this is how you do it. You look at a real world problem. you try to express that as a physics problem. You understand? If it's a mechanical thing, what do? You use laws of physics to first define that problem. Okay? And then what do? You express that physics problem as a mathematical problem. Let's say a differential equation. Right? And then you seek a mathematical solution to that. All mathematical problems have a mathematical, not all, but most of these differential equations have purely mathematical solutions. They don't bother about a physics-based solution. So there is abstract mathematics where they are absolutely not bothered about what the physics means, what it means physically. So you define that as a differential equation or a mathematical problem using laws of physics. You have to apply laws of physics to make it a mathematical problem. And then you seek a mathematical solution. Then you interpret that as physics. What is the physical meaning of that when applied to your practical problem? Two problems in the field of aerospace engineering and electrical engineering may have the same mathematical statement. May have the same differential equation representing that problem. You may get the same solution for those two problems, but the physical interpretation is going to be different. Okay. So this is the basis for our study of space mechanics. Okay. So these are the laws. What do you mean by laws? What do you understand by laws? It's a proved hypothesis. What else do you have in mind? What do you mean by proved?
Universally applicable.
Okay.
You understand it to be true?
Huh?
You understand it to be true?
You understand to be true. Okay. Can you prove laws mathematically?
Yes.
You cannot prove laws mathematically. So that is the real meaning of a law. For example, Newton's laws can only be expressed mathematically. You cannot arrive at Newton's laws starting from somewhere. Okay? So that is where we start. So when Kepler proposed his three laws, we'll study Kepler's laws. When Kepler proposed his three laws of his three famous laws, right? Those were the laws. We couldn't arrive at Kepler's laws starting somewhere else. Experimentally, you can verify the law again and again, but you cannot prove that that law is true. If you want to really prove, you have to use mathematics. So when we do orbital mechanics, this was Newton's law of universal gravitation. And this is what he just thought. So this is what his intuition was, that this is how it should be. And when we applied it to, many times when we applied it, it kept on being true. Okay. Similarly, Newton's second law of motion, or Newton's three laws of motion, in our study, for this course, Newton's second law is very, very important. Okay, although Newton's first and second laws, the third law are also important, but we will use this law more extensively. So you have, this is F net is equal to mass into acceleration. And you have to, very important note is, Newton's laws are only applicable in an inertial reference. Okay.
Give an example of which is that in inertial reference.
Yeah, we'll talk about inertial reference here. So this you have to understand. Okay, F net is equal to, now also it's important that you how do you define Newton's law? Newton's second law? The definition? That is not the definition. That is not the statement of Newton's law.
Force equal mass times
Reduction in momentum is
Right. If an external force causes change in linear momentum. Okay. So now, if you take the derivative of this, what are you going to get? You're going to right. So this is, you apply the product rule. So what happened to this quantity?
This is derivative.
So why is this quantity not here?
Mass isn't changing.
Mass is not changing. When we are studying orbital mechanics, as long as we are in space, this law applies. But when we are taking off of the ground, when we are doing actually rocket dynamics, this is an incomplete loop. You have to account for this mass change. Only then you get a lift off. If you don't account for this mass change, so what is changing in a rocket?
The fuel.
The fuel is constantly, there is mass flow, right? The fuel is constantly being depleted. That mass flow actually gives you that thrust. Okay. Only in the beginning there is a equivalent opposite reaction. What happens in the beginning? The rocket is pushing off of the ground, right? But after that, after it lifts off, after it takes off the ground, this is the major contributing factor which will take it into space. The orbiting body, we only talk about orbiting body. We don't talk much about the launch. Orbiting body is not really changing in mass. Is orbiting body changing? Does orbiting body change in mass?
No. Well, yes.
Specific things.
But is the only law you change?
Not changing direction.
I don't think so.
See, when you do the orbit change, what do? You use again thrusters. At that point, again, this applies. Only this is the only means of causing an external thrust. Okay, that is, so if you, that thrust, there is no external thrust actually, it's an internal mass change which causes change in force, and that is how you move out of the orbit. Orbit change, orbit maneuvers, when we do, we use this again, this principle. This now, during that time, this does not apply. Okay. Your impulse, just in this context, impulse is defined as integration of, it's very simple actually. So integral of force over time is the impulse. In rockets, in orbiting bodies, you're going to mostly use impulsive force. Have you seen gravity, the movie Gravity?
Yes.
So you see, there is only small impulses of thrust. So that is impulses of thrust.
So,
That,
doesn't that change your position like it just?
right, it changes the, we'll talk about that. It changes the position actually.
So, can you explain the last part means?
It just means, so what I did was I just substituted this, okay? Assuming mass is the same, mass is constant. It is just mv2 minus v1, right? So you can say m is the same, right? v2 minus v1 is delta v. So delta v is impulse, net impulse, I net over m. So impulse, in other words, is simply this. Okay, assuming F net is constant. This is we define angular momentum as r cross. You understand what angular momentum is. You understand what is moment force, right? Moment force is just a distance into force, right? So that is the moment r. So this is that moment r. Okay, r is the moment r, and this is how you define angular momentum. Did we define linear momentum? Did we define linear momentum?
That's right. Linear reversal.
Right. This is linear momentum. MV is linear momentum. R cross MV is angular momentum.
What does that say by the M? What does it say by the M?
Which M? This.
Oh, yeah.
So this is net momentum, net angular momentum. Angular momentum is always defined with respect to a point O. This may be constant, this may be one value, but depending on where this, how you define this R, this M will change. You understand? You remember that famous statement, give me
Give me your 4, your 3.
give me a space to stand and a long lever, and I'll move the earth. You remember this? Okay. What it meant was, if this distance is long enough, you can actually, you know the lever action, right? The lever action. If you're trying to carry a weight, if you have a really long, massless rod in your hand, that weight can be negligible. You understand? So that is what it meant. If you are given really long this thing to move earth and a place to stand, you can actually, by applying very less force, you can move earth.
So if I was standing on the moon,
Huh?
if I was standing on the moon and I had a rod long enough to reach Earth, I could push on Earth.
Probably like
Should be a certain angle.
The rod has to be heavy. That's just the rod.
Alright, this H naught you have to just give this a little bit of a stare. Look at this and look at this, okay? Just like net force or force acting on an object of mass m causes linear momentum, change in linear momentum. A torque or a moment acting on a body of mass m causes angular momentum. You understand?
Can you say that one more time?
See, when you push something, that is a linear force. Okay? Linear force causes, what are the first laws say? Body in mass stays in mass, body in motion. Yeah. So this is that. That is the first law. Right? The body in motion or body at rest continues to stay in that state unless acted upon by an external force. Right? You can define that in terms of external torque. What is the difference between torque and force?
Torque is
Rotation.
distance times force.
Torque causes rotational motion. Force causes linear motion. We have to understand, as space engineers, as aerospace engineers, we have to be very meticulous, we have to be very careful about understanding these two kinds of motion. So this is actually Euler's law. Okay? It's nothing but rotational motion of Newton's second law. Got it? Do you see the similarities? You can look at this. You can look at this this part and this part. O is simply about which point you are defining the moment. MO net is just a net moment is equal to R cross MV or change in R cross MV. Do you get it? I can just write this as, let me just do this. So R cross, this is the side.
What is it? Can you search your computer?
Huh?
Can you pull your computer in some close a little bit? Is that possible?
It's recording actually. If I change it, it won't. Yeah.
It's on YouTube.
Oh, okay. Okay, never mind.
So if you have, sorry. R cross d over dt of mv can be written as d over dt of R cross mv. Okay. Now here is your vector knowledge comes into application. What is R cross mv?
That's the M.
That is actually this angular momentum. That is how we define angular momentum. Okay. Now why can we write it like this? If I split this open, what am I going to get? I'm going to get R cross M d over dt of V. Okay. This is V. Minus d over dt of R cross with M V. Okay, you're with me? If you have a cross product like this, cross product is anti-commutative. So when you take the derivative of a cross product, it will be A cross B. Derivative of A cross B is always equal to A crossed with derivative of B minus B. Okay? So if it is just a dot product, you generally do a plus. If it is product rule, you generally do a plus. Cross product, this sign changes. That's all. So if you apply this, we'll continue here. You have R cross with d over dt of V. What is this? Minus d over dt of R is V, correct? It is V cross MV. This is 0. Why is this 0? A vector crossed with itself is 0 because the cross product is, how do you define cross product? How do you define cross product?
The determinant.
Right, but you have a sine theta in there, right?
So
The
magnitude of two vectors gives you another vector.
You have, when you define, this is 0 because you just have, A cross B, it is AB sine theta, and theta is the angle between A and B. Here it is angle between V and B. What is angle between the same vector? 0. And sine theta is, sine 0 is 0. So that is the reason this is 0. Cross product of any, of two vectors, of parallel vectors is always 0 because of the sine theta term. Dot product of orthogonal vectors is 0 because there is a cosine theta there. Cosine theta, cosine of 90 is 0. We'll do a little bit of relative motion. H naught is angular momentum and H naught is simply R cross with M P. Okay. Angular momentum is defined as R cross M V. Yes, sir.
Why did you capitalize the unit vectors?
I don't capitalize unit vectors. It's not always the case. If you see, these unit vectors are not capitalized.
Does it matter?
Huh?
Does it matter?
It doesn't matter. When you represent that cap is most important. The underline and cap is important. Cap, you understand the cap. Caret. Yes. So that is important. So let's say, let's look at time derivative of moving vectors, okay? So what we have here is, you have an inertial reference frame, okay? Inertial reference frame is a non-accelerating frame. We have discussed this, right? So for example, if Earth were not rotating about its own axis, right? And if you attached a frame to that, that would be, for all practical purposes, that would be an inertial reference frame. Okay? A frame which is rotating along with Earth. You understand when I say rotating, please understand it is rotating about its own axis. Revolving is okay if you attach, because as we have discussed, right, there is theoretically there is no inertial reference frame because everything is accelerating about something, right? But in the larger context, if you attach a frame which is not rotating with Earth, that would be a inertial reference frame. Okay. So what we have here is an inertial reference frame. So assuming this is non-accelerating, this is a moving frame. Okay. And let's say this is my vector b. I want to define the time derivative of vector b. Okay. Now, this vector b, see, you understand that b can be expressed. Vector b can be expressed as bx I plus b y j plus b z. Okay, or it can be expressed as b bx I plus b y j plus b z. Do you understand the difference between these two vectors?
Are you saying that that B up top, the object is moving up?
No, it's just a vector.
Okay.
It could be a position vector, it could be a velocity vector. It is just a vector.
Can you explain the difference one more time, please?
So this b is the same vector. Okay, it's just one vector. It's depicting, let's say, position or velocity or acceleration. But it is expressed in, this is expressed in this inertial reference frame. Okay, so the components are bx in cap I direction. This is cap I. by in cap j. bz in cap k. So this vector is coordinatized in this reference frame. The components are in this reference frame. Here, it's coordinatized in this reference. So you see these are small ijk. Now if you take the derivative of b over dt of b, here what is, it will be b x or find this directly. Okay, you understand what I did here? If I take the derivative of this, just this component alone, what would it be? It would be change in the component itself and change in I, right? Both these are vectors. This is a basis vector, this is just a component, this is a scalar, right? So the position could be changing and this basis vector could be changing. So these two capture the mathematical derivative of this. These two capture the mathematical derivative of this. These two capture the mathematical derivative, complete derivative of this. Okay? You get it? It is just applying product rule here. However, this is 0. This is 0 because see I is not changing. I, J, K are not changing. That is how you define your inertial reference frame. Because it is defined as an inertial reference frame. What does this mean? That those lines drawn like that? Fixed. It is attached to something. So those are not changing. Right? But here this is a moving frame. If you coordinatize the vector in a moving frame, you have to account for how this frame is changing as well. Okay? So if you want to define, let's say for a simple example, you're in an aircraft, right? You could be moving in the aircraft. Your relative position in the aircraft is changing. Correct? That is this change. The component change is that change.
So that one is if you're in the plane, your body moving with respect to the plane.
Yes. So here what is happening here is you are not in an aircraft. You're coordinatized, or you're in an aircraft, but you're coordinatized not in an aircraft frame. You're coordinatized in a fixed frame, a station which is able to figure out how you're moving. Okay? Regardless of the reference, it doesn't need to really figure out where the aircraft is. It perfectly knows how you're moving with respect to that tracking or that radar. You understand? Here what is happening is there's a station which is tracking the aircraft, how the aircraft is moving, and inside the aircraft your motion is being tracked. You understand? So what is happening here is this is the change, your local change. You see Bx, By, Bz as a dot or as a derivative, which means your position. So this is coordinatized in this. Okay? This, the first line, accounts for your local change in the aircraft. The second line accounts for the change in the aircraft frame itself. You get it? So this is a moving frame. This is how you define, this is very how you understand the time derivative of moving vectors. Okay? So what we do is, this di by dt can be expressed as omega crossed with I. Bj dt expressed as omega cross j dk over dt, where omega is
Cool.
okay. So this dot, I dot, j dot, and k dot, that is d over dt of I. Right? If I substitute that, so let's call this is A, this is B. Okay? From B, d over dt of B is equal to d x I d I, sorry. Plus dx into omega cross I So this is for any vector B. Okay. You account for the relative change in that vector. Okay. Plus this accounts for the change in the reference frame itself. So here think about it as this as being this B changing, locally changing, okay, or you moving locally in an airplane. And this accounts for the airplane itself rotating. Got it?
Now, can you repeat that, please?
This accounts for your motion within a moving frame. You can think about a car as well. Alright? And this accounts for the motion of the vehicle itself or the motion of the airplane. Now, if this is position vector. So you have, if you have d square b over dt, this would be again d over dt of db over dt plus omega cross with b, right? So this gets a little bit tricky, you have to be careful. So what you do here is, you get d over dt of db over dt plus d over dt of omega cross with b. Okay, so this would be, again this is relative. Okay. You can say d square dt over b plus omega cross with d over dt of b minus so you have something like this, right? Now think about this as, this is one vector, right? Correct? So if you say this is vector small b, what you need to do is d square b over dt is equal to, you apply this law to that. It is d over dt of b relative plus omega cross with b.
What is that law mean again?
Huh?
That law, the one that you got? That's the.
Any vector, the derivative of any vector b is always expressed as, first its local derivative, which is relative, plus the derivative of the changing frame. Okay? So if I define this as vector small b, this is how it's going to roll out. And now if I substitute, what am I going to get? d over dt of d over dt of b plus omega cross with b, okay, plus omega cross with d over dt of b plus omega cross with b. What did I do here? You able to follow?
No.
So you understand this? Derivative of the double derivative of b is the derivative of this quantity, right? So what I did was I just substituted this here, right? I defined that as this is just a vector b. Derivative of any vector b, small b, is equal to derivative of small b relative plus omega small crossed with small b. Okay? I have to substitute for b, small b. Small b is this plus omega cross b. Right? Plus omega, cap omega crossed with this b. That small b again is this. Got it? So you have d square dt b, okay, plus d over dt of omega cross b plus omega cross with d over dt of b plus omega cross with omega cross with b. Alright, let's do one thing. You guys want an extra session this week? Can we do an extra session? Tomorrow?
No.
We ain't gonna figure it
We're going on Thursday.
out.
Thursday? Thursday what time? Huh? 8 o'clock?
We're in class